Welcome back. Next, we will do NAND gate. Okay. So in this NAND gate, what you have to understand is the same as how we build a circuit. So what is the Boolean expression for NAND gate? Y equal to A dot B. A B bar. So this is the NAND gate expression. So understand few points here. So we have to start all the time with the pull down devices. In CMOS, we have some pull down section. And we have pull up section. Pull up section. In pull up, we will have all PMOS devices. All PMOS devices in pull up. In pull down, we will have NMOS devices. And this pull up device, this will be connected to here VDD. And pull down will be connected to ground. And here they will be connected. The separation is connected. This is demarcation line. From here, you take the output. Whatever the output is there, you take from here. Now their gates are connected like this. So you give any input here. Your input is here. So you have to start with the pull down. So that is with NMOS devices. Now how to connect is another thing. So if dot convention is there, then devices are connected in series. Okay. If plus is there, that is or is there, instead of this dot here, if we have plus, then we have to connect devices in parallel. That is another point that you have to remember. Once your pull down devices is done, so this is, let's put here, this is the one. This whole discussion is one, point number one. So we have pull down devices. In pull down, we have NMOS devices, and then pull up section, wherein we have PMOS devices. We connect this PMOS and NMOS devices from where the connection is there. From there, you take the output, and their gates are connected. Okay. And pull up devices are connected to VDD, and pull down devices are connected to ground. Okay. That discussion is point number one. Second discussion is this one. You have to start with the pull down devices, and you have to see under this bar, whatever the expression is there, if that expression having dot, then devices needs to be connected in series. How to connect in series, I will demonstrate. If plus is there, instead of dot, if here is a plus, if here is a plus, A plus B bar, plus is there. So start with, connect the devices in parallel. Once this under bar, whatever is there, that is done. So that is pull down section is done. Now what you have to do, third point is, take the dual of the expression. This under bar, whatever the expression is there, of that expression, you have to take the dual. So you have A dot B. Of that dual will be A plus B. Okay. Now, once this dual is taken, then you have to go for pull-up devices. Again, the same rule. When you go to the pull-up devices, rule is same. What is that rule? If dot is there, then connect devices in series. If plus is there, then connect the devices in parallel. Okay. That's how you do. By default, CMOS will give inverted output. By default, CMOS will give this inverted output. So, if bar is there already, then directly if you take the way it is shown, like you have done with pull up, you have done with pull down. Now you have connected your gates also. Then directly whatever the output you take, that is correct because the bar is there. So by default, CMOS technology will give the inverted output. Let's say, what if bar is not there? This bar is not there. Let's say you have A, B, like that. There's no bar. This discussion still valid that you start with pull down, then you go for pull up by following this rule. The dot is there means series connection, plus is there means parallel connection. Then you take the dual of that given expression. Again, in pull-up section also, you will follow for dot series connection for plus parallel connection. Everything is same. Since output is coming in inverted form, but this is not in inverted form. This given one is not inverted form because there is no bar. So at the output side, you have to connect one inverter. Inverter in earlier video we have seen. So this is our inverter. This is our inverter. So just connect at the output. Output, that is why you connect here and take actual output here. This is your actual output. This is applicable when your expression is not having the bar. Just you have to put a inverter before this, I mean after this Y. Okay, this Y needs to be connected to the inverter. Then that inverter output is what actual output is. Okay, so pause this video, listen to this one, go back in this recording, and then listen to this what I'm saying here. You will understand. So now I will give the demo. So to give the demo, let's go to the example that is NAND gate. So NAND gate expression is like this, A, B. So what I have said, we have to start with the pull down devices. To connect the pull down devices, we have to see how the expression is. So in pull down, NMOS devices will come. So here, every variable is one device. So this is A is one device, B is another device. Two devices are there. So in pull down, we need two NMOSs because NMOS devices will be there in pull down section. Series means like this. This is how series connection is. Okay. So connect them in series. This is what series connection is. Now, this one will be for A, the gate, and this is for B. Now, you can put B here, then A here also, not a problem, anywhere, but one input, one variable will be for one device. That's how it is. Second, what I said, we have to take a dual of that expression. And you don't consider this bar, just under bar, whatever is there. You have AB, right? The dual of that is A plus B. Now you will go to the pull-up section. So here pull-up section. In pull-up section, again, you have to follow that rule. Dot, if dot is there, then in series, if plus is there in parallel. So since here plus is there after dual, you have the plus. So in parallel, you have to connect. This is one device. In pull-up, you will have the PMOS device. This is PMOS device. Parallel means like this. Side by side like this. And then you connect them. You connect here like this, and you connect this like this. And this is A, and this is B. In any order you can keep here. You can keep here A and then here B. Okay. So now what is being said earlier discussion, we have to connect this one too, right? So just connect here. Where this connection is established, from there you have to take the output. So this point is what our Y is. Okay. And further, what has been said in earlier discussion, this pull-up devices will be connected to the VDD. So we have to connect this one to the VDD here. Here, we connect this one to V, D, and D. And then pull down section will be connected to the ground here. This is connected to the ground. And further, what has been said, we have the bulk terminal. This is the bulk terminal, and this is the bulk terminal here. So that bulk terminal needs to be connected to the source in PMOS case. Here is the source. And in NMOS case, source is here. This is your bulk. and this is the source. So here you can, and another here. So you have this bulk here. This bulk is connected to the source here, like that. So now what is been said earlier, by default, CMOS technology will give inverted output, right? So this output is in inverted form. So it means this is inverted form. So that is what we are, NAND gate is. So you don't need to plug in the inverter at the output of this, after this Y. You don't need to put an inverter and don't need to connect this Y to that inverter and take the output of that inverter. So that is not required. If it is AND gate, then that is required. If it is AND gate, then you have to develop one inverter here. So this is your PMOS. PMOS gate is connected to NMOS here. And this output requires to be connected to this gates here. And then you take the output here. This will give you the AND gate output. Okay. So let's now do this one in LTSpice. So do in LTSpice, here LTSpice, double click that. When this is the interface. So in this interface, you have to click this one for circuit, this is the sheet where you work the work for circuit. So what is required here? According to this discussion, two NMOS devices are required. So let us get the two NMOS devices. So here NMOS 4, that is 4-terminal device. One is, mouse, if you wheel, if you are down, if you are, moving, or if you are moving up. So zoom out is happening when down. When you move up your mouse cursor, wheel, then it is, this is zoom in happening. Okay. Zoom in, zoom out. This is zoom out. Down, wheel I am making down. When I make up, roll this wheel upwards, then it is zoom in. Okay. So I need two NMOS. One NMOS I will keep here, and another NMOS will be here just underneath. Now I need two PMOS devices, but how I am connecting? In parallel, I have to connect. So side by side, I have to keep. So this is one PMOS. Here I keep, and another PMOS. Now I have to connect with wire. So take the wire, connect this point little down, click there, hover your mouse, exactly this point. So take that, diversion here, click here, and then go up. Now click here, connect this. Now click here, connect this. Now click this point, click there, then hover your mouse, come down, click there and come down. Now, this one little extension, gate of this little extension here, and left click, and then here I want to stop, left click and then right click, like that. Here left click, there I want to stop, left click and then right click. Here left click, there I want to stop, left click and right click, like that. Now here little wire I will extend upwards. Here click, go up, left click and then right click. And here also little wire down, left click and then right click. Now I have to connect the terminals, this bulk terminal. So this bulk terminal, left click, our mouse, left click, go up, left click, come this side and then left click. Here also same thing. And here this requires to be connected to the source. So source is here. And this requires to be connected to the source. Source is here. So now I take this ground and ground is connected here. And I need a VDD here. So for that, I will use this net label. So net label, this is label here or net label. Here VDD I am giving, VDD. and place it here, just left click. Now A, B. So I just take A and place everywhere here. Later I will edit here, here, and here, and here. So now I am editing. To edit, take your mouse cursor over that label, right click, then you can edit. This is B. And here also one I have to edit. This is B. This has become B. So now my AB is here and another AB is here. And I take wire and extend this connection from this point to out here for taking the output. Okay. So that is done. Now to have a full view of that, you have to click on this. So that's how you get the full view. And to get rid of this, wire, escape. If you press, then you can get rid of that. Now, we need voltage sources for A and B for VDD. So go to component. Here voltage is there. Voltage. Click OK. So place here for one is VDD, one is for A, one is for B. So now go to this label net and here VDD, type VDD, place here. You can place here, but extend wire little bit up. That is better. Little bit up. And here also wire little bit down. Left click, go there. There I want to stop. Left click, right click. Here, left click, come down, and then right click. Left click, go up, left click, right click. Click, left click, come down, left click, and then right click. So now you can connect here label net, VDD. VDD. This is VDD. And I will place this later, I will edit here, here. And here I have to connect the ground. So to connect the ground, this ground is here and here. And so if you're finding this overlap, then go to this one, move, select that portion and move here like this, away from that. Same here also, like that. Now I have to give the values. VDD, right click, see the mouse cursor, how it is changing. Like this now, when I take here, it is changing this way. Right click there. Now give 5. Click OK. So now 5 volts, this VDD. Now for this, I have to edit this, right? This labels. Right click, edit as a A. Now without wires, everywhere this connection is established from this voltage source. Here, here. Now it's same thing here also. Edit this VDD as B. Now connection is established from this point to everywhere wherever B is there. So now give the value here, right click, go to advanced, go to pulse. Now before that, I just wanted to discuss something. Pay attention here. This is important, very important. So when you are doing the NAND gate, you have 2-input NAND gate. You have A, B 2 inputs. So 0, 0, 0, 1, 1, 0, 1, 1. So it means this is tabular form. If I draw a timing diagram, for 2 time intervals, it is 0. 1 time interval, another time interval. For 2 intervals, it is high. So this is high for 1 time interval and another time interval. This is A. Now the B, if you take, alternate, it is low, high, low, high. So this is low and high. Again low and then high. So it means what? If A is having this time period, B is having only this time period. So in this A, we can set 2 this B signal, 1 B, This is another. Same, it is repeating here. It is periodic. So it means if it is 20 nanoseconds period, this period is only 10 nanoseconds. That is the meaning. So this is required. Why? Because come to this one. When you go to this, uh, applying this A, advanced, go to pulse. Here 5, you have given that pulse. Okay. But how long it will be on? So let's say if it is on for 10 nanoseconds. S shouldn't be given. S is already here. Then what is the period of that A? Just now we calculated. That is 20 nanoseconds. So on period 10 means, and the total period is 20 means. Obviously, off period will be 10 nanoseconds. Okay? Understand this fact. Stop the video, little bit go back and understand what I'm saying. So here, this is the pulse height here. This is the pulse height, that is 5 volts. So we are mentioning only on period as a 20 nanoseconds. And total time period also we are mentioning, that is 20 nanoseconds. On period, 10 nanoseconds. Total 20 nanoseconds. So remaining time is only 10, right? That 10 is for this off period. This is for on period. So that's how it is here. Total on 10 nanoseconds. Total period is 20 nanoseconds. Meaning that off period is 10 nanoseconds. Click OK. Now for this B. B, go to advanced. Again, see, like this cursor shape should come. Right click. Go to advanced. Go to pulse. Here again, voltage on is 5, that is maximum height of that pulse, and T on is half. Here 10 nanoseconds means this will be for 5 nanoseconds, and the total period is 10 nanoseconds. So here we demonstrated this one. On period 5, total period is here 10 nanoseconds. So obviously the remaining will be for off period. So now this is what we have done here. Okay. Now click OK. So it means you have given little bit. We will move this one here. Click here, just hover mouse. Okay. Now your circuit is ready and we have to label this output also. So let us label output as a Y. This one. Here. Place it here and click, left click. And then to save this file, save as. Here on desktop, I have created already one folder. You also have to create one folder. So in my case, it is lab demos. Inside that, again, you have to create another folder. So I have to create here another folder, that is AND gate. Sorry, NAND gate. And gate. So click that. Select that folder. Open this one. There properly you have to name the file. So if you are removing extension, no problem. It will be taking like here it is .asc only. So now NAND gate, then save. So after saving, you click on this run. So it is transient analysis. So let us run this till 10 nanoseconds, just 10 N. Okay, click OK. Now to vertically place this one window, then tile vertically, like this it will come. So what is that we wanted to display here? We wanted to display here this A value. Anywhere you can place this one. About this cursor shape, I already spoke in the first video, inverter video. If it is changing like this, it is current. If it is voltage. This way, it is voltage. We want voltage. So, and A is here, A is here, A is here. Anywhere you can click, no problem. The same voltage will. So A and then we want B, and we want out. So now you can maximize also this one by clicking here. So it is maximized now. So let me close this one. So now I wanted to separate this. So right click, add plot pane. Now drag this VA here. So I now VB and VY overlapped. Right click here, add plot pane. Now take this VA further up here. Now get this VB here. Okay. Now click here. See the mouse cursor, how it is changing when you bring this one to VA. Now you can see that the cursor change here. It is 1. The moment when it is changing to 1, left click and drag this anywhere like this. So if you place it here, this is, we are having 1 and this is 1. That is VA1. This is high here, right? Pulse is high. And here also high. So what is expected according to NAND gate? 0 is expected. You can see here it is down, low, 0. So this explanation is what required by the student in external paper. Now, if you look at this one here, it is 0 here. And this is still 1. So you can drag this one here. This is 1. This is 0. That is VA is 1. VB is 0. So 1, 0 means NAND gate will give the 1, right? So this is 1. Now drag this further here. This is 0 and this is 1. Your NAND gate will give 1 out. Now drag this further here. Both are 0, 0. This is 0, this is 0. So your NAND gate will give 1. So it means it is functionally correct. And then observe here carefully. This is schematic .asc and this .raw is a raw file. That is for waveform. So how to close this simulation? Simply, you should not be here. You should be here and then close this one. There are two here closing, right? One is this bigger one. The other is lower one. This is smaller one. So smaller one, if you close, you have closed actually the simulation. That's how you close the simulation. Okay. So that completes our NAND gate demonstration. Please complete this, practice this, pause the video. All aspects I have covered. So kindly practice now. Okay then. Thank you.